Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. In this session I will discuss this power supply circuit. It is a 5 volt 1 ampere charger circuit, although it is not a very complicated circuit. But why I selected this circuit to explain that in this circuit there is no optocoupler used. It is without optocoupler. How it will regulate the voltage, how it will monitor the current, how we can trace a circuit and how to understand a circuit. This is a very basic requirement to take approach in troubleshooting and repair process, not specific to this circuit, any type of circuit. When we want to repair it and we don't have any circuit diagram, any service manual, any schematic, any blueprint, locate its main IC, check its part number and try to locate its data sheet. Here is DP1801. Now go to Google and search here DP1801 IC data sheet. Here is PDF, check DP1801 IC. We will check this one. DP1801B Quasi-Resonant PSR CC CV PWM Power Switch. DP1801 integrates functions and protections of under voltage lockout, VDD, over voltage protection, OCP, over current limiting, over current protection, short load protection, thermal shutdown, VDD clamping, and here is its typical application circuit. When we locate data sheet or when we locate application note for that IC, that will give approximately 99% similar circuit to the practical layout. AC input, bridge rectifier, one capacitor, then DC line filter, second capacitor, then here is startup resistor, VCC capacitor or VDD capacitor. It is connected to VDD pin. Primary winding, auxiliary winding, and this is secondary winding. In secondary winding there is diode, capacitor, dummy load resistor, and here is auxiliary winding. We can see one diode that is connected to same VDD capacitor points, VCC capacitor point, and auxiliary voltage are directly provided to voltage divider network, and it will go to pin number 2, that is feedback pin. Pin 3 is not connected. Pin number 4 is current sense. 5 and 6 number pins are drive pins. These are driving primary winding. In the parallel to primary winding there is diode, capacitor and resistor, RCD snubber circuit. When this switch is off, this RCD snubber will demagnetize the core. Now we will see its pin out, and here is pin function. Let's see its block diagram. We can see this is drive pin, pin 5 and 6, C pin, then current sense, an external resistor that is connected here at current sense pin, that is current sense resistor, RS. That is basically power ground for the transformer, for the transistor that will drive to transformer. Here is VDD clamp for 28 volt maximum protection, VDD over voltage protection. Then this circuit, it is UVLO and overload protection. Here is feedback circuit. It will monitor the voltage value coming from auxiliary winding, and it will monitor the current. This will provide switching frequency. Finally, this PWM set reset switch for current limiting. This set reset, it will provide full frequency or half frequency. Maximum voltage 800 volt, input voltage DC line, and DC current, drive current maximum 800 milliampere. We can say primary current maximum 800 milliamperes. VDD voltage and different values. If you see this soldering temperature, in my last 2-3 videos I discussed how we can solder or desolder ICs. In each case we need to consult the data sheet to find the temperature. For this IC, 260 degrees centigrade for 10 seconds. So this lead temperature is basically soldering temperature. You can find in the data sheet. Maximum 260°C temperature can be provided for maximum 10 seconds. Here is switching frequency 70 kHz and minimum switching frequency 35 kHz. Because it is fixed frequency oscillator, but it will adjust its frequency depending on the load. In overcurrent condition, like that. Different parameters are mentioned here. We have no concern with that parameters. Here is function of this IC. Let's back to main page. Now we will check physical circuit. Same as mentioned in the diagram, that there is input. In the input there is fuse, and if you see, here is fuse, that is this one, 10R half watt fuse resistor. Most of the time in data sheets there is sample circuit with values, but in this data sheet it is showing components without values. Fuse, then it is reaching to bridge rectifier. When we are testing, if we find voltage at input terminals, this one and this one, second step, check AC voltage at these 2 points. If we cannot find voltage here, then we can remove AC input voltage and we can check continuity between these 2 points across this fuse. If AC input voltage are present, then we can check DC voltage at these 2 points. It is output terminal of bridge rectifier. Here is first capacitor, 4.7 microfarad, 400 volts. Then red, it is inductor, 2200 microhenry or 2.2 millihenry. Then these positive voltage are reaching to this point. Here are 2 nodes. This node, it is connected to this capacitor, class Y capacitor, 102M. Second end of this capacitor is connected to output circuit. It will remove the switching noises. Any type of common mode noise in secondary side will be grounded from here. At this point, inductor. Same as in the diagram. Here is second capacitor. Negative terminal of both capacitors are connected together. Positive is connected here. Filtered DC voltage will reach here. So this inductor, the first function will provide regulation in the DC line, and second, it will block all noises to reverse back to the bridge rectifier and to the line. So switching noises will be blocked here. Then negative line is reaching here and positive line is reaching here. Same as shown in the circuit diagram, 104 resistor, that is 100K resistor, and this capacitor. These both are in parallel. Then this diode, A7 diode SMD, RCD. Then this 100 ohms resistor, it is current limiting resistor. This resistor is not shown in the sample circuit. These positive voltage are reaching to RCD snubber, and in parallel there is transformer winding. This is positive end of this winding and this is drive pin. If we check this point, it is connected to negative terminal. And here is 1R40, 1.4 ohms resistor. It is current sense resistor. So negative side voltage, negative line is reaching to pin number 4. It is power ground for its power transistor in this portion, and it will drive this transformer primary winding. Negative terminal resistor, emitter of this power BJT or MOSFET whatsoever, drive pin, winding, positive terminal. So this is the circuit. Pin 3 not connected as shown in the sample circuit, pin 1 and 2. If we see pin 1, it is coming out from here and it is reaching to this diode cathode pin, and same point is connected to this capacitor, that is VCC capacitor C3 positive pin. And if we check this positive line from underside of bridge rectifier, it is reaching to this 2 mega ohms, 2 mega ohms, 4 mega ohms resistor, two resistors in series, 2 plus 2, 4, it is reaching to positive terminal. As shown in sample circuit, the same positive voltage are applied to this capacitor. This capacitor will take time to charge. So this is soft start circuit. It will provide delay time to power on this IC. In that delay time, these capacitors will hold charge. If you are applying 220 volt, 311 volt will present at this capacitor and this capacitor. Meantime, same 312 volt, 311 volt will reach here, and it will allow a very slow charging, because 2 mega plus 2 mega 4 mega ohms resistor is providing charging voltage to this capacitor. This voltage will reach to pin number 1. VDD pin, positive voltage are reaching here, and if we see this pin, pin number 8, pin 7 is missing, not connected. Pin 8 is reaching to this point, from underside of this resistor, it is reaching to negative terminal. So as mentioned in the sample circuit, that pin number 8 is ground pin, ground reached, delayed voltage are reached at pin number 1, this IC will take start. It will start to make pulses. That time current will flow from capacitor negative terminal to resistor, this pin winding positive terminal. How much current is flowing in this channel? The same dropped voltage at this pin will be provided to its chip circuit, its control circuit. If we see its block diagram, pin number 4 mentioned here as a current sense input pin. It is current sense plus power ground, because here at current sense pin there is 1.4 ohms resistor that is connected to ground line. So voltage dropped at that pin will be provided to this circuit. Here is 0.5 volt reference. Anytime the current flowing here will cause to drop voltage above than 0.5 volt, this circuit will reach an LEB, leading edge blinking. That time this transistor will start to skip pulses until the voltage are dropped below 0.5 volt. If there is anything wrong, if there is overload, voltage will increase than 0.5 volt at this pin that are dropped between this point. This point, if we see, it is connected to pin number 8, that is ground pin, chip ground. Between chip ground and pin number 4, if there is difference of 0.5 volt, this IC will move in LEB, leading edge blinking. When it started to make pulses switching in the primary winding, it will store energy in the winding, and here is secondary side, this winding, and here is another winding of this transformer, that is auxiliary winding. One end of this winding is connected to ground pin. The same ground is connected to this capacitor ground, VCC capacitor ground. Auxiliary winding second end, one side is connected to this diode and it is rectifying voltage. Positive voltage are reaching to capacitor positive terminal, that is VDD capacitor, and same voltage are reaching as we mentioned at pin number 1. But here 1802 2491 18K resistor and 2490 ohms resistor, these are connected in series. This point to this point, this is ground terminal, chip ground, and this is voltage divider junction. These two resistors are dividing voltage. This junction is connected to feedback pin. It will monitor the voltage, how much voltage are here. Now the voltage monitoring theory will start from this point. Here is secondary winding. This end is connected to ground point. Here are two capacitors in parallel. In my last video I repaired this charger and I found these capacitors damaged. Negative terminal, these 2 points, these are body of this USB connector, and then negative terminal of this capacitor and one end of this class Y capacitor. And same voltage are reaching to this dummy load resistor, 560 ohms resistor. Secondary winding this side is coming to this Schottky rectifier SS34. It is reaching to this point directly to the capacitor positive terminal and this capacitor positive terminal. So both capacitors are connected in parallel to increase capacitance and to decrease the ESR value. Here is 470 micro 10 volt capacitor, same 470 10 volt. So both capacitors will become in parallel. Capacitors will around 940, voltage will remain 10 volt, but the ESR value will decrease. This resistor, dummy load resistor, is connected between positive to this resistor will cause to draw minimum current in this section so that this IC will remain in good working condition. If there is no load, this IC will sense voltage from this pin. Suppose at this pin we have 5 volt and here we can say 0.05 volt are here, 50 millivolt. That time this IC will become to know that there is no load. If we connect load here, it will cause to flow more current in secondary because it is flyback topology. First it will store energy in the core, in the primary winding, in turn on time. When it will turn off, that time that magnetic field will collapse. That will create voltage in secondary and in this winding. Now this IC is off. We are taking voltage in off time here and here. If there is no load, we can say in turn on time, here was just only 50 millivolt drop at this pin. And we are taking 5 volt at this capacitor because this collapsing magnetic field is creating voltage here and here. When we will connect load here now, that load will cause to flow more current in this winding. That will, because this winding and this winding are in phase. This winding is out of phase, 180 degree opposite, and these are in direction. That means if here current will flow, this magnetic field will cause to induce more voltage here. Here we connected load. Due to load, reverse EMF will be generated in this winding. So voltage value here at this capacitor will increase. When voltage will increase, same voltage are reaching to this pin. That is voltage divider network pin. From here, this IC will become to know that how much load is connected. For that purpose, it will increase some more duty cycle to increase more switching to maintain the voltage here. This increased voltage will inform this IC that the load is connected here. How much load is connected here? Half ampere. At half ampere, here will some more voltage. Maybe we will receive 7 volt here. At no load, 5 volt. At medium load, 6 volt. Just for example, at full load, 1 ampere output load, we will receive 7 volt. If we connect any short circuit or the load is driving more current, might be here we will receive 8 volt. When 8 volt, this IC will check that there is over voltage protection. There is overload condition. Same time, when there is overload condition, when it will drive next pulse to maintain voltage here in the output, it will drive some more duration pulse. That time more current will flow in this winding and here more voltage will drop. When this pin will increase above than 0.5 volt, its internal leading edge blanking circuit will enable. That will cut the pulses so that this IC will control its current. By adjusting the value of this resistor, we can limit the output current at our required value. In any case, if this IC will increase above than 800 milliampere, this IC will damage. To protect this circuit, to protect this IC, this pin, current sense pin, must be observed carefully. So this is the working of this circuit. Let's monitor the voltage by adding some load. If you don't have good experience in electronics, never do this experiment or never repair it, because we will deal with live voltage. First I will check DC voltage without load. At VCC capacitor, that is here. .98 volt at 0 ampere, that are output voltage. Let's monitor voltage here. (9 volt). We have 9 volt in case of there is no load. Now let's connect load. I connected load. 0.44 ampere current is flowing in the circuit now as a load current. Now we will monitor the voltage here. Now the voltage are 12.21. We can see the voltage increased at VCC capacitor. These voltage will inform the IC that the load is connected. I explained just theoretically that at no load 5 volt, with load 6 volt, full load 7 volt. Same way here. With no load 9 volt, with half load 0.44 ampere, we are receiving 12 volts. Let's connect some more load. .26 ampere. .89. This time it will monitor the pulses on its pin number 4. Why the voltage are not increased 2 more? Because this time the IC is shifted in leading edge blanking. Now I connected 0.6 ampere load. Let's check voltage now. .85. This time it is working within range. When the pulses at pin number 4 will increase than 0.5 volt, this IC will determine that there is overcurrent condition. .95 volt across this rectifier. These are blocking voltage. When we are testing any circuit, we can test voltage across rectifier or we can test voltage across capacitor. The same. 5.34 volt. 5.31 volt. Here are slightly high voltage. Here is 0.531 volt, here is 0.535, because these voltage are across this rectifier and winding, and here we are receiving voltage across this capacitor. So this is the basic concept of understanding a circuit. If this video is informative for you, give a thumb up. If you have any question, please write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.